Hi, in today's demo, we're going to be combining RAPIDS and Sagemaker together to accelerate hyperparameter optimization in the cloud. RAPIDS is an open source ecosystem of data science libraries that have been accelerated for the GPU, and Sagemaker is a machine learning service provided by Amazon that allows data scientists to do their development in interactive Jupyter notebooks and then deploy them using a high-level API to the vast cloud infrastructure. In our example, we're going to be leveraging a large public data set of flight statistics and train a model to predict flight arrival delays. Our workflow is the first step, and so we're going to go ahead and define the classic steps of model, or rather data preparation, model training, model evaluation, and then lastly just saving our result. And with that workflow in hand, we're going to append it to a RAPIDS-based container and publish it to the Elastic Container Registry. And in addition to that, we'll define the search space of our hyperparameter optimization, essentially the bounds of the possible models that we'd like to explore over. And with everything ready, we're going to go ahead and send this over to Sagemaker using our Pythonic API. And Sagemaker will take our container and spray it around and spin up multiple compute instances, each of which will get a unique combination of hyperparameters that will be evaluated. And eventually it will find the best model, which we can then take and publish. The combination of these two tools is extremely powerful and offers both acceleration within a node by leveraging the number of cores that the GPU offers, as well as across nodes by allowing Sagemaker to run parallel experiments. And so when these powers combine, we get really impressive real-world results. In the context of the dataset that we chose, we're seeing about a 4.5x reduction in cost and about a 12x reduction in time. The time reduction is particularly impactful to data scientists, as something that might seem prohibitive and take multiple days can just be reduced to hours. And these kinds of cost and speed savings are typical of the kind of performance numbers that we see for RAPIDS and Amazon customers like Capital One. So without further ado, let's go ahead and get started so you can actually launch into this notebook and play around with it yourself. Fortunately, the notebook has been included in the Sagemaker examples, so it can be easily triggered from the native user interface. And so we're going to go ahead and do that next. Great, so let's begin with the Amazon Management Console as our starting point. Once here, we go ahead and select Sagemaker from the machine learning options. And next, we're going to need to trigger the start of a notebook instance where we're going to be doing our work from. I already have one of these running, but let's go ahead and go through the steps of creating a new one. So we click on Create Notebook Instance, and we fill out really just this one value, which is the name of the instance. For the instance type, we'll leave it as default, which is a T2 medium, relatively lightweight instance that does not have a GPU. This costs about 4 cents an hour, so it's a perfect medium for us to do our development in without having to worry about costs. The instances that we're going to be renting once we actually trigger our HPO work are going to be fired up by Sagemaker behind the scenes, and so we don't have to really worry about having an accelerated notebook instance type for the moment. All of the rest of the settings can be left in their default state, and go ahead and click Create Notebook Instance. Since I've already got one of those running, I'm just going to switch to that tab. And this is something along the lines of what you might expect to see. This is just the Jupyter launcher screen that you'll land into, where you can typically select a kernel to start working in. Because we are leveraging our specific notebook choice here, we're going to go ahead and click this little brain icon on the left-hand side, which will open up a selection pane for sample notebooks, and scroll down to Hyperparameter Tuning, and then select RAPIDS Sagemaker HPO. This will create a prompt that shows you a preview of the notebook, and then you can go ahead and click Create a Copy to actually start one. In this prompt, it'll tell you all of the assets that are required to be copied into your workspace, and go ahead and click Create a Copy. Again, I have this running already, so I'm just going to switch tabs and launch into it. And this is the notebook that you should see once you have everything set up. This is just a reminder that we're going to be leveraging RAPIDS and SageMaker, and we expect to get scaling both within a node and across nodes. We covered this graphic already, the 3 steps that we're going to be jumping through. So without further ado, let's actually get into the content of the notebook. The first step here is a form of a preamble where we're just getting our SageMaker settings correct. So this is the execution role in our session. And we can see that our account number is this, and then we're in the US East 1 region. Below, we allow you to make some key choices for setting the configuration settings of the hyperparameter optimization. The defaults we've set are what we might consider to be a small HPO run, where we're only using a year of the data set and running a relatively low number of cross-validation folds with a low number of total experiments and a low number of parallel workers. If you were to do this for production grade, you would most likely have a larger data set, do more cross-validation folds, use multiple GPUs instead of a single GPU, increase the number of experiments and the parallel workers. You're, of course, feel free to change these settings in a way that is suitable to you. These are just 2 suggested configurations, and we'll start with the small one just because this one I think will allow you to get to a result and you can kind of experience the acceleration without having to necessarily jump in and go all the way to the deep level of acceleration that's possible with a large HPO. So as we mentioned, for the dataset and bucket choice, we'll just pick 1 year. There's options here for 1, 3, and 10 years as well. And the number of samples in our dataset grows. So in case of the 1 year, we'll be using 7.2 million flights. You can go all the way up to 63 million flights with 10 years. And then for the bucket selection, this is mostly done for you here. One consideration is that we've made this data publicly available in the US East 1 as well as the US West 2 regions. If you plan to be in a region other than this, you might have to create a replica there. Or also if you plan to bring your own data set, you should feel free to change these settings. For the algorithm choice, we invite you to try either XGBoost or random forest. Both are supported in our code paths. XGBoost is the one that we have set for by default. And then for cross-validation, we have a somewhat reasonable number of 3 cross-validation folds, where this is the number of times that the training and test data will be remixed and reshuffled so that we can make sure the results that we're finding are actually robust and not just lucky in terms of how the training and test data got split. For compute choice, here we can pick the level of parallelization that we want, and starting with perhaps the least parallel option, this is the single CPU choice, where we leverage pandas and scikit-learn in this code path. Pandas and scikit-learn are very popular data science libraries that you may have already seen, and pandas is really useful for data frame manipulation, where scikit-learn is a library that has a lot of machine learning tools. In the RAPIDS world, we have sort of the clones of these library with GPU acceleration. So the pandas equivalent is cuDF or CUDA data frame, and the scikit-learn equivalent is cuML or CUDA machine learning. And so in our demo here, we're going to use just a single GPU version of this. But if you were to use a large data set like the 10-year flights, you would want to use the multi-GPU choice so that you can leverage the memory of multiple GPU workers together. Similarly, for the CPU side, if you start getting into large data sets, you want to leverage multi-CPU. And when we go from single to multi, both in the CPU and GPU case, we add Dask to the mix, and Dask is a really great library for parallel Python parallelization. And so we invite you to check out the code. It's going to be something that we quickly point you to, but for the most part, here is where you get to play around with different levels of acceleration. And so we encourage you to start with the single GPU mode first, but then you're welcome to try the different variations. Next, we have to define the search space for our hyperparameter tuning, and this is where you can pick the space of possible models that you want to admit when you're looking and doing your actual experimentation. And here we've just set some popular parameters and their ranges, but you're welcome to look into the documentation for the XGBoost and random forest respectively if you want to append additional hyperparameters to search over. In the case of maximum depth, we go between trees of depth 5 and 15. And for the size of the forest, we're either looking at 100 or 500 trees. Anywhere in there is fine. And then the number of features that are used when constructing each of the individual decision nodes can vary between 0.1 and 1. Another key choice is the type of search that we're going to be performing. Here we've selected random search, where every successive run in SageMaker is going to be independent from all of its predecessors. So the choices of hyperparameters are going to be not affected by things that have happened in the past. You can swap this out for Bayesian search, which tries to make educated guesses about where to look next based off of what has happened in the past using a form of regression. Here is the experiment scale. The defaults are 10 and 2, and this is the number of total experiments you'd like to run, and this is how many workers work in parallel to get to this number of total runs. And so our defaults for the small scale are, again, 10 and 2. If you were to ramp these up to production grade, you might see something like 110 here. The more experiments that you do, the better chances you have of finding a really performant model that you can deploy. This parameter here is just a sort of a safety guard to make sure that none of our jobs runs for more than 24 hours. And then we're almost done. And so here, based off the choices you've made above, we have a little function that recommends an instance type, so that if you set your code choice to be GPU based, and then you have a certain number of years for your data set, it will recommend an instance that has been tested and should work for that configuration. You're of course welcome to use something other than the instances that we recommend, but this is just a helper function to help you make sure that you have something that will run. Lastly, the spot instances flag is something that we encourage you to keep as true. This typically leads to about 60 to 70% of cost savings, and you can read more about spot instances, but effectively they're a way to reduce cost by allowing you to use instances in which you could theoretically be kicked off of. In practice, we find that out of 100 jobs you might get kicked off of 1, but that's really a small price to pay for the tremendous cost savings that you experience. So next, we sort of just validate our choices and let you see all the decisions that you've made so far. And with that in hand, we actually get to the next important step, which is the building of the workflow. The data set that we leverage, again, is the airline domestic on-time performance statistics that have been kept by the Bureau of Transportation since the late 80s. And it has lots of interesting features in it. Things like the locations and distance of a flight, who was the carrier, the scheduled departure and arrival times, the difference between the scheduled and arrival times, and then a binary encoded version of whether or not the flight was late in arriving, which will eventually end up being our target variable, the one that we're trying to predict. For those who are curious, we have all of the code available here in the train.py and the RAPIDS Cloud ML.py, and this is where you would go to see sort of what's happening behind the scenes with the workflow. Just as an aside, we also have a notebook that goes through and sort of shows you the data science steps that we took step by step, so you can investigate and look at the raw data values of various flights. You can filter and visualize things like delays coming out of Atlanta versus delays coming out of, let's say, Seattle. You could also look at things like feature correlations. You could plot the decision trees that get learned and also do a comparison of the CPU versus GPU for the individual parts of the machine learning workflow. But we'll sort of skip that for now and leave that as an exercise for the interested reader. Again, just kind of take our word for it that we've built a machine learning workflow that is fairly straightforward, and we're just showing how we can take a workflow and accelerate it for the purposes of HPO here. So let's get back on track. And so the next step is to take our work and build a container / Sagemaker Estimator with it. And so for the purposes of that, we're going to be taking a RAPIDS-based container, augmenting it with the Sagemaker training toolkit, and then lastly adding our custom code to it, which is again the ETL training and scoring function that we've written. We're going to do a Docker build using this recipe, and then lastly push this to the Elastic Container Registry so that it can be accessible to SageMaker. The section 2 here of the notebook goes through and allows you to select which RAPIDS base image you want to use, either the stable version or the nightly version that gets built every time that a new PR gets pushed to GitHub. Either choice is fine. I'm going to kind of skip through some of these details, and just in case you're curious, you can look at we're sort of dynamically building the Docker file here, where we start with the base container, we augment it with SageMaker training, and then we just copy in our 2 little Python functions that have our training script and the library that the training script calls into, and lastly tell SageMaker to run the training script when it runs. And so here's our full Docker file. We go ahead and pull down the base container on which our Docker file is built on, and then build our actual Docker file. You can look at the steps in detail, but we're going to skip that for now. We log into the Elastic Container Registry and create, basically just push our container to it. This may take you a little bit of time the first time you run it, but subsequently it should be quite fast. And with all of that done, we can now wrap our container into what's known as a Sagemaker Estimator using the Python API, where we just tell Sagemaker that use this image that we just built that we pushed up to the Elastic Container Registry, and then it uses a little bit of the previous choices that we made, like the whether or not to use spot instances and our Sagemaker session and role, etc. We go ahead and summarize our choices once again and kick off a Estimator Fit Run. This will just use the default values in the code to sort of kick the tires and make sure that things can run end to end. And so when we do this, it will actually trigger instance launch and download our data. You'll see a lot of output from the SageMaker training, and then you'll see essentially the output from our custom code. The key thing to see here is that it ran to completion. We ran it for 3 cross-validation folds and reached an accuracy number about 92 with some default values. And we also, since we used a spot instance, we were able to get significant savings. So far we've built our workflow, we've containerized it, and we've made sure that it can actually run in SageMaker. Next, we're going to actually do the important work of running with many variations or running hyperparameter optimization to find the champion combination of hyperparameters that we can then take and deploy. So once again, a little bit of work before we can kick things off. One thing to note here is that we need to tell SageMaker how to look for the performance in the logs of our output. And so here we're writing sort of a regular expression to tell it to look for the string final score, which will be an indicator of the best performance that we produced given a run of our estimator. This metric will get passed into the settings here of the SageMaker hyperparameter tuner object, in addition to our estimator that we built above. So essentially, with our estimator in hand, with the metric definitions in hand, the hyperparameter ranges in hand, the search strategy, the maximum jobs, and the max parallel jobs we're finally ready to do one large hyperparameter tuning job run. Since this is going to be a lot of compute, we once again summarize our choices and ask the user whether or not they're sure that they want to kick this off. Once they actually do kick this off, it will take some time, and so this is a waiting call to block until the HPO completes. And since I've already got this sort of pre-baked, we can skip actually waiting for it to complete and jump straight to the results. So here we see that our best score was 93.59 on this data set, and these are the optimal hyperparameters that were used for that. So with a tree depth of 6 and using about 366 trees and a large number of features when making decisions. You can look at the details of all of the jobs that were run. Again, since we were doing sort of a relatively small scale HPO, this was only 10 jobs. But nonetheless, you can see their details here. And one useful thing to do once you've run HPO is to actually take the best model and save it and use it for production. So we've also given you some code here that allows you to go and download that best model based off of the results above. And here we actually go ahead and grab that best model, extract it, sort of uncompress it, and sort of recreate a XGBoost model that, essentially we're bringing this trained model back into memory so it can be used again. And here we have, just as a sanity check, 2 different dataset examples, one which we know was an on-time flight and one which was a late arrival. And so the on-time example is taken from 2019, whereas the late example is from 2018. The most relevant feature here is the fact that this example, this first flight, left 9 minutes early, whereas this other one left almost 2 hours late. So using these 2 examples, we should be able to feed them into our trained model and get predictions that are reasonable. And so indeed, when we take this trained model and do a predict of the on-time example, we see that it has a very low probability of being late, whereas when we do the same thing for the late example, it has a very high probability of being late. And so just to take this all to completion, we can take this trained model and actually deploy it to an instance. So here we take our estimator and we call .deploy on it and pick a GPU instance type to run on. And this will take a little bit of time. Essentially, SageMaker will spin up a whole new instance. It'll take our container and now run it in serving mode. And we've written just a very lightweight Flask server to handle incoming requests and feed them through our trained model. And so below here, what we've done is we've just taken our late example and wrapped it into a minimal amount of code that allows us to send this over the network in a serialized fashion. So this is what we're calling our serialized payload. And we take this predictor that we just built here and we ask it to predict our serialized payload using, for its model, the best HPO model that we found. And we know what this best HPO model is since we just ran the whole results summary up above. And so with that, once again, we see that for this late example, it has a very high probability of arrival delay based off of our model's opinion, which matches what we did when we were running the local test. So effectively, we now have an endpoint that's able to do prediction, and you can either pass in individual examples to it, or you can pass in batch data. And so with that, we've essentially gone from start to finish. We've built a RAPIDS machine learning workflow. We've containerized it as a SageMaker Estimator, and we've run HPO experiments to find the best hyperparameters for our model. The accuracy we reached was not the highest you can go, just because we only ran 10 experiments. But if you're interested, you could read more about the experiments that we ran for a larger scale. And there we got to a higher accuracy, which was shown here, and also with significant speed up and reduction in cost compared to running on CPUs. So One last thing I think I'd like to mention is that if you're curious, you could look at, there's an additional notebook called HPO Analysis Tuning Job Results that's published by Sagemaker, and there's a link to it here. And so if you were to look at that notebook, it would take your job and you could do plots like this where you can compare the performance of optimizing various hyperparameters. So in this particular case, it's showing that as you increase the depth of the decision tree, you get higher accuracy. And so you could look at that for all the different hyperparameters you run, so maximum depth, or number of estimators, or number of features. And again, with things like the number of features, you notice that there's a linear trend upward. So the more features you use to make decisions, the higher the performance is on the ultimate metric that you care about. So with all of that, I'd like to thank you for your time and attention. Feel free to reach out to us if you have questions, and hope to hear from you soon. Take care.